Hey everyone, welcome to the velocity versus time graphical analysis video. That's a big long title, but oh well. So in the last video, we talked about this object's position versus time. This is the corresponding velocity versus time graph, okay? You may recall that in between points A and B, there was a concave up curve, right? Concave up, something like this, means that the slope at all points on that curve, in other words, the tangent line, slope, tangent line, same thing, is increasing in value, right? On the position versus time graph, that is written as a velocity or a speed. Delta x over delta t. And so that increase in slope value corresponds exactly to what we have here, right? The value for the velocity at all points in time is getting greater and greater and greater. In other words, it's getting faster and faster. It's speeding up. When an object speeds up, do you have an acceleration? Yes, you do, right? That is the definition of an acceleration, a change in speed or a change in velocity. And so, this change in velocity from 1 second to 3 seconds turns out to be constant, right? And in fact, in all problems, in this course at least, you will have a constant change in speed, right? The velocity versus time graph, you'll never see a curve, right? That means the acceleration value is changing, and that's known as a jerk. We won't really cover that, okay? So just for, just so you know, you'll always see a linear change in speed, if that makes sense. So let's see. Let's do this. At 1 second, the value for the velocity is 0, right? At 1.5, it's 1 meter per second. At 2 seconds, it is 2 meters per second. At 2.5 seconds, it is 3 meters per second. And 3 seconds, it's 4 meters per second. So the rise over run, regardless of what ratio you use, is always the same. So that is by definition an acceleration. A change in speed divided by a change in time. And so in this case, it turns out to be about change in speed. Let's go at 2 seconds. That's, 2 divided by delta t, which was 1 second. So this turns out to be an acceleration of 2, keeping units in there, 2 meters per second divided by 1 second gives us 2 meters per second squared, right? And you can do that for any combination, just keeping sure that you have those two perpendicular, okay? So those two equations, those two definitions are very, very important in this early stage, right? Chapter 2, those are some of the most important equations. Okay? That's the definition of what we'll use for a majority of the rest of our weeks, okay? So that's between points A and B. Between points B and C, what's happening to the slope of velocity? Well, it's not changing, right? It's a horizontal slope. It's a slope of 0. By the way, you can ignore these arrows. I took screenshots of this one big x, v, and a of t graph thing, so that's why they're kind of chopped off. But I will show you the big picture at the very end. So just ignore these arrows for right now, okay? Between points B and C, the slope is 0, so it's not moving. Well, sorry, back up. It's not accelerating, all right? So let's put that in there. That's very important to note. So in there, it is not accelerating. Because the velocity is not changing over time. However, it is still moving forward. It's still moving at some speed. That speed is 4 meters per second. Okay? So don't think that if the velocity versus time graph, if that's horizontal, it's not moving, right? It's moving at a constant speed. And by the way, over here, I should put what's going on. This is accelerating. In other words, speeding up. And we can do it in the positive direction, right? In fact, this is all happening in the plus x direction. Okay, so at point C, what's happening to this object? Well, now the velocity versus time graph is, well, decreasing in value. So the value for the velocity or speed is decreasing. Still moving forward. That's important here. It's still moving forward. It's just getting slower and slower and slower. So you might say it's slowing down. Right? So over here, it's slowing down or decelerating. Well, let's still moving forward in the plus x direction. Excuse me. Now, compare that value of the deceleration, right? That change in speed compared to what was over here between A and B. The time interval is just 1 second, right? The time interval over here was 2 seconds. The delta V, the change in speed interval, is now, what was that? Actually, let's just go ahead and write it out. So between t equals 1 to 3 seconds, let's see what happens. The acceleration equals delta V over delta t, right? So delta V, we have 4 minus 0 divided by 3 minus 1. And so here we have 4 thirds, or 1.33 meters per second squared. Right? For t equals 8 to 9 seconds, the acceleration is 9 minus 8 divided by, oh, I'm sorry, whoops. That's time. Delta V is 0 minus 4 divided by 9 minus 8. There we go. And so we have a negative 4 divided by 1. We have negative 4 meters per second squared. Did that right? 4 minus 0, 3 minus 1. 3 minus 1 is not 3, that is 2. I apologize. If you were just yelling at your computer screen, I'm sorry. 3 minus 1 is definitely 2. I can math, I promise. There we go. Okay, so now we can compare the accelerations of both time intervals, right? The magnitude of the acceleration over here is greater than the magnitude of the acceleration over here, right? In fact, it's twice as much. Magnitude of 4, magnitude of 2. But this is negative because it's slowing down to a stop. Over here is positive. It's speeding up, okay? You can also see that because the slope is steeper between 8 and 9 seconds than over here, right? If the slope is steeper, the acceleration value or the acceleration magnitude is greater, okay? And that's what the math shows us. Okay? So overall, from points A to D, this particle is, well, going from a stop and then speeding up at some rate and then moving at a constant speed for 5 seconds and then quickly decelerating back down to a stop. Okay? So in the next video, we'll talk about the acceleration versus time graph. Thanks for watching.